Hello and welcome to a video on amplifier types. I decided to do this video before we get to multi-stage amplifiers and later on feedback. And that is, you need to know the different amplifier types that exist and how loading them um, affects the gain of each before we can tackle feedback or multi-stage amplifiers or the cascading of amplifiers. So each amplifier has a place in the world, and combinations of them can create various amplifier types. Okay, so we're first going to look at Thevenin a little bit and Norton, and then the four amplifier types. Most people will be familiar and comfortable with the voltage amplifier and how we load a voltage amplifier, but what happens when we have current amplifiers, transconductance amplifiers, or transresistance amplifiers? Um, transconductance you should have heard of when we were doing common emitter amplifiers and such. And that is because it is a transconductance amplifier, not really a voltage amplifier, which we convert to a voltage amplifier by placing in the collector resistor. So you can convert amplifiers from one form to another by adding a resistance or something. So that can be done. So this is just a quick look at the loading of our amplifiers when we have different kinds, and then the next video will be on multi-stage amplifiers. Right. So a Thevenin model for a voltage input, you will typically have your signal, the signal resistor, and then the input of your amplifier. So plain and simple, a Thevenin model is a voltage source and a resistor, right? So going into an amplifier, we have voltage division going in, and the ideal case is if the input impedance of your amplifier is infinite, the input and the signal voltage will be exactly the same. Okay, so when designing for a voltage amplifier, this is one thing to remember. You want the input impedance of the amplifier to be infinitely large for maximum voltage transfer. Okay, we can also use Thevenin to model the voltage output from an amplifier. So you have your voltage source, you have output impedance of your amplifier, and the moment that you add a load, the gain typically drops, and that is because we have this voltage division going on here. If you measure with an infinite load right here at the output, you will measure actually V out. Right, same with when Z out is 0. So the ideal output impedance for a voltage amplifier would be 0. Then the voltage transferred to the load will be exactly the same as the voltage at the output of amplifier. So maximum gain from in to out, right? So if this is 0, it seems not to be there. So that is why you want to design for a very low output impedance of an amplifier. So if we quickly take a look at the common emitter amplifier, the common emitter amplifier has a large input impedance, or it can have a large input impedance. So we can satisfy this kind of easily. But the moment that we add a load to our common emitter amplifier and it's a small-ish load, our gain drops significantly. That is because the output impedance of a common emitter amplifier is quite high. So we have losses internal to the amplifier, and then the remainder goes to the load. Okay, so a common emitter is not the ideal voltage amplifier. One that is the ideal voltage amplifier would be the common collector amp, but it has no gain. The gain is 1. So that is more of a driver circuit. But its output impedance is low, so it ideally can drive a load. So combining those two concepts, you can actually build a perfect voltage amplifier. Right. So whenever we have to deal with voltage on in, on or out, we are looking at voltage dividers like this. Right. Norton models. Norton is typically a current source modeled with a impedance in parallel with it. So for current amplifiers, the output impedance needs to be extremely large. A perfect Norton source, its output impedance is infinite. And why would it be infinite? Because current will rather flow into a resistor which is much less in size than, let's say, this R signal right here. Okay, same with the output of amplifier. So this goes for input and output for currents. So the current flowing into this resistor is then the current divider between these two resistances. So the positions just changes of a resistor. So where it would have been Zin over Zin plus R sig for the voltage amplifier, we now have R sig standing on top for current division. So the perfect input to a current amplifier would be an input impedance of 0. Then everything can flow into that amplifier and not go into this R sig right here. Same with the output of a current amplifier. If this output impedance goes to infinite, it technically does not exist and all the current can flow into the load resistor. Right, so current division is the main thing, or main how we calculate loading effects for currents in and out of amplifier. So let's start with a current amplifier. So the model for a current amplifier will then be a signal in parallel with a resistor. The gain will be in amps per amps. Now if this input impedance is 0, this will disappear and we have R sig over R sig and everything will enter the amplifier. And if the output impedance here is infinite, this R load will become insignificant to the output impedances right here, and we will have 1 multiplied by 1. So then there is no loading effects. Right, then the old voltage amplifier, gain in volts per volts. If Zin is infinite, everything will sit here. And if Z out is 0, everything will sit across the load right there. Okay, so plain voltage division equations. Now, transconductance amplifiers. That is when you have a voltage in and a current out. So, doesn't this look familiar? This should look like the hybrid pi model of the BJT to you. So if the input impedance is fairly large, everything should sit right here. And if Z out is extremely high, think of this as R out or R out in parallel with RC. Then we can have maximum current transfer to a load resistor. Okay, but typically we use this for voltage amplification. So we have major losses when dealing with our common emitter amplifier. Right, so the total gain here in the end would be this transconductance right here multiplied by the voltage division on the input and the current division on the output. This can easily be converted to our voltage amplifier if we just multiply this with our output impedance. Oh, actually Z out, but if we multiply this with Z out, we get our output voltage. So if you'll notice right here, if we add our load, which is our output loading at this point, this is a parallel combination of R load and R out, and then it will be a voltage amplifier. So you can convert between your amplifier types, or if you're looking at transconductance or voltage gain like that, and always remember that transconductance is in amps per volts. So amps per volts, and if we multiply that with volts over amps, which is a resistance, we can have our output voltage, our voltage amplification. Right. So the main goal of transconductance amplifiers is to convert voltage into current. Transresistance amplifiers. Gain is in volts per amps and it converts current into voltage. So we should have a current input going into some input impedance. So ideally this should go to 0. If that goes to 0, we have best input loading, and if output impedance goes to 0, we have a best output loading. Everything goes to the load like that. Right, this can also be converted to a voltage amplifier, and that is by multiplying with 1 over the input impedance of this amplifier. And those are the four amplifier types and how they get affected by loading. So if there's a voltage, okay, if it's for either one input or output, just remember to use a voltage divider for loading effects, and if it's a current input or output, you need to use current division for loading effects. Right, and those are the four amplifiers and the loading of them. Thank you for watching and see you in the next video.